Section 2.1, a preview of calculus. In this section, we're going to talk about the two key problems that led to the initial formulation of calculus. We have the tangent problem, and we have the area problem. Now, in this section, we're just going to do a very quick overview of the problems and the mathematics that went into their solutions, but it's going to take us the entire semester to really understand the calculus that came out of these problems. Let's start by talking about the tangent problem of differential calculus. With linear functions, rate of change is really easy to calculate because it's constant for everywhere along that function. And that's because linear functions are perfectly straight lines. So let's talk about the rate of change here. If I were to pick this point, the y-intercept, I could write the coordinates out as 0 for x and 3 for y. And if I want to talk about the rate of change, one way to do that is to say, how does the output change with the input changing exactly 1 unit? So I would allow myself to advance 1 unit in the positive x direction. My point would no longer be at 0, 3. It would have to move all the way down the line until it reached its new x value at x equals 1, and the corresponding y value would have to drop down to y equals 1. And so what happened was I allowed myself to move forward 1 unit in x, and that caused us to move down 2 units in y. So if we wanted to calculate our rate of change, we look at the change. I'm going to use this triangle, which we call delta. We look at the change in y values divided by the change in x values. You've seen this before as slope. In other words, we have like our rise over our run. So between these 2 points, we can calculate our rate of change. We can see that the change in y was 2 units, and we went down 2 units. So our change in y is a -2. And then we can look at our run, or the change in x. We moved x 1 unit in the positive direction, so our change in x is +1. Therefore, this linear function has a rate of change -2. And it doesn't matter what points we pick on this line, we will get the exact same rate of change value anywhere. So let's take another point. Maybe at x equals 2, y equals -1. That's this point. And if I allow myself to move forward in the positive x direction exactly 1 unit, the new output would be at x equals 3, y equals -3. And again, if I look at my rate of change, we have moved 2 units down, so we have risen -2, or we fell 2, and we moved 1 unit in the positive x direction. So our rate of change would look like a -2 for the change in y, a +1 for the change in x, leaving us with the same number for the rate of change. So linear functions have this really simple way of calculating the rate of change, and you can do it between any pair of points you want. In fact, if I were to pick this top point, let's use different colors here so we can keep track. Let's say I want to calculate the rate of change between these 2 points. On a linear function, we can do that, not a problem. So I would look at the rate of change between 0, 3 and 3, -3. That's going to take us down 1, 2, 3, 4, 5, 6 units in the y direction. So our change in y looks like -6. And then we need to look at the change in the x. That's going to take us 1, 2, 3 units in the positive x direction. So our delta x is going to look like +3. And when we simplify that, we again get -2. So linear functions, super easy to calculate the rate of change. However, we know that there are more functions out there than just straight perfect lines. There are nonlinear functions, like the one that we have graphed on the right side of the screen. Maybe you recognize that as the function x squared. Nice little standard quadratic. If I wanted to talk about how this function changes from one point to the next, it can get a little more complicated. Let's pick our y-intercept. It's actually the origin. And if I allow myself to advance 1 unit in the positive x direction, I follow along that curve until I'm at x equals 1, and I can see that the y value is at positive 1 as well. So we're at 1, 1. Well, the change in y, we went from 0 to 1, so our change in y is 1. Our change in x went from 0 to 1 as well, so our change in x is 1. That tells us we have a slope of 1. But if I were to pick two different points, let's go ahead and continue using the origin, but let's use the point at x equals 2. At x equals 2, y is equal to 4, so we're all the way up here on our function. And if I wanted to calculate the change in y, I went from 0 to 4, that's a positive 4 change. And the change in x, I went from 0 to 2, that's a positive 2 change. That simplifies to 2. So unlike a linear function, we can't just simply calculate the rate of change by picking 2 points on the graph and calculating the slope between them. And that's because it's not a constant rate of change. So when we are talking about nonlinear functions, we need to be specific about where we are on the function. That way, when we talk about the rate of change, we know that it's only about that specific area or that specific section of the graph. It doesn't talk about the entire function like it used to with linear functions. So in this case, we're going to have to create a new term called like an instantaneous rate of change. That way we know that if we're at the point 0, 0 and we're talking about a rate of change, we're talking about how the function changes down there. Or maybe if we're at -2, +4, we can talk about how the function is changing over here. But it's changing differently in each of these points. So this tangent problem is basically saying we want to know how to talk about rate of change for things that aren't perfect straight lines. And the solution to this actually uses straight lines. So we're going to approximate a rate of change by picking 2 points on our function. And we're going to pick one of those points to be like our anchor point. This is the point where we are actually asking the question, what's the rate of change right here? This other point is just a point that's been advanced further up along the curve. We're going to pick these 2 points, one anchor point and then another point on the curve, and we're going to draw a line between them. This line is called the secant line. We draw a line because remember, lines, linear functions, they're really easy to calculate rate of change for. So we can create these secant lines, and we can find the slope of that secant line, and we can use that slope as an approximation for the rate of change at our anchor point. Now, if you don't like to be wrong often, many of us don't like to be wrong, you might say, is that actually a good approximation? I mean, that line, the blue line, is not perfectly lined up with the gold line. So maybe we can do better than that. And you're right. If I take this point that's further down the curve and I bring it closer to my anchor point, I can create another secant line. And this one will be a better approximation. Notice that the green line here does a better job of lining up with the gold line than the blue one did. And if you're happy with that, you might say, well, let's take this even further. Let's bring that green point even closer to the anchor point. And that's exactly where we're going with this. We're going to take the points and bring them closer and closer together. So although these are both secant lines, the blue line and the green line, they're both secant lines. As we bring the points closer and closer, eventually they'll be right on top of the anchor point. And the limit is where we're bringing the points together. So we're approaching the other point, we're approaching the anchor point. And as we do that approach, we create something called the tangent line. The tangent line lines up really, really well with our nonlinear function. Notice that for just a close area around our anchor point, the line is completely on top of our function. So that's a pretty good approximation for that portion of the curve. So the tangent problem gave us these new ideas about a secant line and about a tangent line. And with these two ideas, we can answer the question about what is the rate of change for a nonlinear function? What's the instantaneous rate of change for a nonlinear function? Some of the problems that you'll do in this section are asking you to find slopes of secant lines. So for example, you'll be given a function, you'll be given the anchor point, and then you're going to find a secant line that connects your anchor point to another point. Maybe these two given points. And we're going to use that as a practice for approximating the rate of change for a function. So if we're looking at the function x squared, and we want to approximate the rate of change near x equals 1, we're going to find secant lines through the point passing at x equals 1 and the other given point. So we're looking at f of x squared. We're looking at what happens to our function when we plug in x equals 1. That spits out the point 1, 1, so that's our anchor point. And then we want to create a secant line using the given point. So we're looking at maybe a graph that looks like x squared. We're looking at the origin would be like right here. We're looking at the point 1, 1, and then the point 2, 4. And we're creating a secant line through those points. Just a rough sketch. Ooh, pretend that line's perfectly straight. Thank you. The secant line that's passing through these 2 points is going to have a slope, and that slope just measures the change in y over the change in x. So change in y over change in x. If we look at our 2 points, we're at 1, 1 and 2, 4. So the change in y from 1 up to 4, we can write that as our 4 minus 1. And then our change in x from 1 to 2, we can write that as 2 minus 1. So we're just using subtraction here to find the difference. And we have 3 over 1. Our rate of change looks like 3. We're going to try that same calculation, but this time we're going to use a given point at 3/2 and 9/4. So we're using the same anchor point. Copy our graph over, function, and we're at the same anchor point 1, 1, but this time we're at 3/2, 9/4. That's actually a little bit closer than the old point, so let's say that the old point was here. Our new point, let's say it's like right here. That is the 3/2, whoops, 9. My 9 looks like a 4. Let's fix that. There we go. All we need to do is calculate our slope again. I'll keep it in blue. So our rate of change will look like the change in y over the change in x. So we're just going to do the calculation again. Our y value for this advanced point is the 9/4. minus the old y value, which was at y equals 1. And then the change in x, our x value is 3/2 minus the original x value, which was at 1. So then we just need to do this calculation. If you want to use a calculator for this, go ahead. I am not here to judge you on your fraction phobias. But remember, if you want to subtract fractions by hand, you just need a common denominator. So 9/4 minus 1, that's the same thing as 9/4 minus 4/4. And then 3/2 minus 1, that's the same thing as 3/2 minus 2/2. I just converted my ones into fraction forms. 9/4 minus 4/4, that leaves us with 5/4. 3/2 minus 2/2 leaves us with 1/2. Now this is not an ideal answer, although it's correct. We want to simplify this the best we can. We have a fraction divided by a fraction. So when two fractions must divide, flip the second and multiply. That's a cute little phrase there. So 5/4 times the reciprocal of 1/2, which is 2/1. That looks like 10/4. Those are both even numbers. We can simplify that again because 5 times 2 is 10 and 2 times 2 is 4. So we can divide off a pair of 2's, leaving us with 5/2. Whew, long-winded, right? But here's what I want to point out, that we use the same function in both cases. We use the same anchor point in both cases. We got a different calculation for the rate of change because we used different points to create our secant line. Now the point that was further away is going to give us a worse approximation than the point that was closer. So 3 was one approximation, 5/2 was another approximation, and since the fraction point was closer to our anchor point, that will be the better approximation for the rate of change.